Hello gang, welcome to week 7. The topic for the week is rational functions, and this may be one of the more difficult weeks to learn the material on your own. I'll acknowledge that to begin with. This is maybe a challenge week if you haven't seen this material before. We've been looking at linear functions, quadratics, and then polynomials. And things are just getting progressively a little more complex. You know, basically, we're looking at first degree polynomials with graphs that are lines, and second degree polynomials with graphs that are parabolas opening up or down, and then general polynomial graphs where we get lots of camel humps, but still the end behavior is the tail either goes down or up, and it's all connected and continuous with local maxes and mins. Well, now we want to look at rational functions. And here we're looking at something in the form f of x equals one of these guys, a polynomial, divided by another polynomial. A ratio of polynomials, which is why they're called rational. Polynomial over polynomial. A simple example of that, well, we've already seen one in one of our basic toolkit functions. The reciprocal function is a polynomial function. Let me look at a shifted version of that. How about this rational function? The polynomial in the numerator is just a constant, 1, but that's a 0 degree polynomial, that counts. And here I've got a linear polynomial in the denominator. But what kind of graph will I generate from this? This one, you know, because you know the graph of 1 over x, and this is just a shifted version of this. So shift 3 units in the positive x direction, and my graph basically looks like this. But look at some of the new characteristics that are possible for the graphs of rational functions, even for something as simple as this one. The end behavior. Notice that as x goes to negative infinity, in other words, scanning the graph this way, I don't have a situation where it's blowing up or blowing down. Instead, what I have is this kind of behaving asymptotically to the x-axis. It's actually just getting closer and closer to 0. We could say as x goes to infinity, f of x goes to 0 or approaches 0. And similarly for the other tail, as x approaches positive infinity, f of x also approaches 0. This is characteristic of a horizontal asymptote. This function has a horizontal asymptote, asymptot, and the horizontal asymptote here is actually the line y equals 0, otherwise known as the x-axis, right? You might also notice that this function has a vertical asymptote, right? The vertical asymptote, vertical line that's an asymptote, is the line x equals 3. That vertical line. And note that that value of x equals 3, is not even in the domain of this function, right? Whereas the polynomials and the linears and the quadratics have all real numbers for their domains. Here, all real numbers except 3, except anything that would cause me to divide by 0. And that also tends to show you where the vertical asymptote or asymptotes will be if I get more than one factor in the denominator. So it gets rather complicated with these kinds of features. Let me do one more quick example. Well, actually one more example, not quick, but I'll move as quickly as I can to give you a sketch in this video. and then we'll come back in the next part and look at another example. Suppose I want to analyze the rational function g of x equals, and I wrote down x squared plus x minus 6, a quadratic polynomial, over x plus 1, another linear polynomial. But here we're looking at a rational function of, suitable complexity to maybe be like quite a few of the ones in your homework. And your problem is generally to analyze the function, figure out its domain, what are the x and y intercepts, what are the asymptotes, vertical, horizontal, or oblique, sometimes called a slant asymptote. You're going to see some asymptotes that are actually lines that have a slope other than 0. And then to be able to hand graph something like this and verify using a calculator. Okay, so I'm going to go through a more elaborate step-by-step procedure with you and give you a handout that you can work with and give you some practice in the weekly assignment. But let me go over this one kind of quickly. I want to look at a factored version. It's real important for this week's homework to be skillful at factoring. It's one of the reasons why we reviewed that recently. Because you're constantly factoring polynomials to understand what's going on with these rational functions. And when I look at this in this equivalent factored form, I notice there are no common factors above and below. You'll see some instances in your homework where you can cancel a factor, but you have to be a little bit careful about the domain issue, and you wind up getting what we'll call a hole in the graph. And I'll give you an example of that in my next video. Stop and look at this and think about intercepts, x and y intercepts. Suppose you were making a xy or xg of x point plotting chart here, and you put in 0 for x. That's going to find you any points on the y-axis, right? It's going to find you y-intercepts. So we put in 0 for x. G of 0 is 0 plus 3 times 0 minus 2. So basically you would just get, I'll write it here, g of 0 would be negative 6 on top, right? 3 times negative 2, and on the bottom I'd get 0 plus 1 is 1. So I guess negative 6, 0, negative 6 is a point on here. And just like any other kind of function formula, you can find the y-intercept by putting 0 in for x, okay? How about any x-intercepts, or zeros of the function? What's going to give me an output of 0 for the whole formula? Well, here you can do a little bit of a trick with rational functions, and remember that fractions are equal to 0 if and only if the numerator is equal to 0. So I can actually kind of ignore the denominator and just say, what values of x are going to give me 0 up here? Because 0 divided by anything will give me a 0 output. So looking at these two factors and setting the numerator equal to 0, I can see that either negative 3 or positive 2 will produce 0 up there, and 0 divided by whatever will give you 0. So this has a couple of x-intercepts. Okay, so starting to look at a graph here, I see x-intercepts at negative 3, 0, and a positive 2, 0, and I see a y-intercept at 0, negative 6, 2, 3, 4, 5, 6. So I've got this for intercepts, okay? How about asymptotes? Well, the vertical asymptote is actually pretty easy to see here. Just like the earlier example, if I divide by 0, there's going to be an undefined value in the actually a value of x that's not even in the domain. So if you think about what g of negative 1 is, oh, wait a minute, you'd have to divide by 0. So it would actually be undefined if you were putting it in this chart. And instead of bothering with that, I'm just going to learn to look at the zeros of the polynomial on the bottom, and if I spot that x equals negative 1, is a place where the denominator is equal to 0, I know that's going to be a vertical asymptote. I'm not going to get a point that falls right on that dotted line as part of my graph. My graph is going to be broken into two parts. There'll be a part over here and a part over here without touching. And then the tails close to the asymptote will either go up along the asymptote or down along the asymptote, one or the other. Okay, let's see. Could there be a horizontal asymptote or even a slant asymptote? We're going to analyze that by looking at the degree in the polynomials. This is the second degree polynomial on top and a first degree on the bottom. And as long as the numerator is 1 degree higher than the denominator, we're going to get an oblique or slant asymptote. That's the case with g of x here. So now I need to do a little side work, okay? I'm going to sort of sneak over here where you can see me, but this is kind of scratch work. You will have some of my math lab problems where you have to do polynomial long division. I think it's in the appendix of the textbook, A3 or something like that, and you get a couple of homework problems where you have to do a polynomial long division. And you'll see examples in my math lab, but this works pretty much like numeric long division. I say, what do I have to multiply x by to get x squared? Got to multiply by x, and I multiply through here, x squared plus x. And I draw this line and I subtract. It's polynomial subtraction. A lot of people do this by changing these two signs and then adding. So the x squareds go away, and here actually the x's do here, which is a little unusual. All I'm left with is minus 6, and I can't get x to go into minus 6 unless I go to something fractional. So I'm going to stop at this point, and here's my quotient and here's my remainder. And what I've shown is that this division here, top polynomial divided by bottom polynomial, it's actually equal to the quotient. In this case, just x, and typically it'll be maybe in the form mx plus b, a first degree polynomial. And then I've got this remainder, so that means really that's the part that still hasn't been divided by x plus 1. This could be plus negative 6 over x plus 1, or just subtract 6 over x plus 1. I'll make it look like negative 6, okay? So basically this could be written in this form using polynomial long division. And let me show you what that tells us about the asymptote. If I look at values of x that are really big, you know, as x goes toward infinity. So I put in bigger and bigger values of x. Look at what happens to the denominator of this fraction. This becomes bigger and bigger. If I put in 100 or 1,000 or a million, this is 101 or 1,001 or 1,000,001. Anyway, it's a big number. And negative 6 divided by a big number is pretty close to 0. This is a kind of a calculus notation way of doing this, but as x goes to infinity, this stuff just gets closer and closer to 0. It becomes negligible. And the whole function behaves a lot like just plain old x plus this thing very close to 0. So the whole function gets increasingly close to x, which is the equation of a line, mx plus b, this is just 1x plus 0. X is the equation of the line as we know from our basic function list. It's the equation of the line that goes through the origin with a slope of 1, not x equals 0, but y equals x. And in this case, this turns out to be an oblique or slant asymptote. Oblique, or a little more slangy, slant asymptote is y equals x in this case. Y equals whatever the quotient is in this division. So I'm going to have a slant asymptote. Let me see if I can just about sketch the graph based on this. I've got an intercept here, an intercept here, intercept here. For instance, on this side, I would maybe want to investigate this with a little bit of point plotting. But I'll bet I have a piece of the graph that looks basically like this. It goes through these two intercepts, and then it approaches this slant asymptote. It'll look more and more like a line. And here it goes down and approaches the vertical line x equal negative 1. And then I've got a point over here. I'm guessing, might want to verify this with some point plotting, but I'm guessing I'll have another chunk of the graph that looks basically like this. And you can verify this by putting this into your calculator. But if you know how to spot this, how to do this. Spotting the intercepts and spotting where the asymptotes is often enough to tell what the graph is going to look like, at least pretty close. And then if we need a little more information, we can do some limited point plotting. I can say, well, what happens when x is equal to 8? And I can go over here and figure out g of 8. But I don't want to do that for 20 different points if I can help it. And I want to be able to pull all this information out about where are the intercepts, what is the what are the asymptotes, and what is the tail behavior like. Okay, I'm going to wrap it up here, and I'll see you in part 2, where we'll look at a handout that you've got that's got step-by-step, I think 6 steps for analyzing and graphing rational functions. And I'll help you fill that out, and then you'll have some practice in the rest of the assignment and in my math lab. Okay?